So the video we're watching right now is from a CD titled The Chemistry of Life. And we're focusing on hydrogen bonding in water and how it affects some of the physical properties of water. So I'm going to start off here by clicking on the hydrogen bonding in water. Turn the faucet on. We'll zoom into the water. And here's 5 water molecules. So not only can water hydrogen bond, but it is also unique in that it can hydrogen bond to 4 neighboring water molecules. So I know it's not showing it here, but remember water has 2 lone pairs of electrons around the oxygen. So it has a Vesper geometry that's tetrahedral. And the 2 lone pair of electrons can hydrogen bond to 2 water molecules that have the hydrogen rotated towards it, because those lone pair electrons are the partially negatively charged side of the water molecule. So they will hydrogen bond to hydrogens of 2 neighboring water molecules, where the hydrogens on that center water molecules will hydrogen bond to oxygen on a neighboring water molecule. So that ability of water to hydrogen bond to 4 other neighboring water molecules is pretty important in some of the properties. So here is showing some of the dynamics of hydrogen bonding. So what we're seeing here is what would be liquid water, where the water molecules are still able to move past each other like liquids can do. And you notice that at any given time, the hydrogen bonds are forming and breaking, but usually there's still at least 2 or 3 hydrogen bonds going to several of the neighboring molecules while other bonds are breaking and forming. So that allows water to behave as one unit. So you're able to like pour water out of a jug, yet it'll still stay all connected together because you're breaking some hydrogen bonds, but there's other hydrogen bonds forming and still intact. So moving on to some of the properties, we're going to come back to this one when we get to lipids. Here's the how water moves up a tree, defying gravity. If we focus here on the tree trunk, we have the blue little balls are our water molecules, and then we have the cell walls. I'm going to zoom in a little further. And what we have 2 different forces, cohesion and adhesion. So the cohesion is the cohesive force that happens between individual water molecules. Adhesion is when the water is attracted to some other substance, and in this case it's the cell wall. So if we focus on the tree, the leaves here, as a water molecule evaporates, it pulls up a water molecule below it, because it's attracted to it by the hydrogen bond. So when one water molecule evaporates, the next one moves into its place because it was like tugged there with the adhesion and cohesion forces. Focusing on surface tension, so here is my water molecule, and what they're showing down here is a water skipper bug that's floating on the top of the water, and they're zooming in on just one particular leg of this water skipper. So that's what this brown blob is here, it's his leg. And notice that the hydrogen bonding on the surface of the water is allowing this water skipper to stay afloat, because for his leg to sink through the water it would have to break all these hydrogen bonds. So water has a fairly strong surface tension because of all the hydrogen bonding that's occurring there at the surface. Water has a very high specific heat, meaning it is able to hold a lot of heat in it, because as water is warming up, it takes a lot of energy to break those hydrogen bonds, because hydrogen bonds are so strong. So when a hydrogen bond is broken, it absorbs that amount of energy it took to break it. So when water starts to cool, those hydrogen bonds that were broken are now starting to reform, and the heat then is slowly given off. So that's why the temperature will vary quite a bit. What it's showing here is the picture on the right is the desert. And if you notice the huge fluctuation in the temperature, at night it gets very cold, and then during the day it gets really, really hot. That's because there's not much water in the desert to help buffer that. If we're here by the ocean, we've got a lot of water, and during the day this water has trapped a lot of heat. So during the night, when it starts to cool down, the hydrogen bonds in the water start to reform and give off some of that heat. So you don't see those drastic temperature changes because of the specific heat in the water. Here's a diagram showing evaporative cooling, and this is what our bodies do. So the picture is showing our skin here getting really pink because it's hot, and what our body does then is it opens up pores and allows the sweat to leave, and sweat is mainly water. So the water molecule absorbs heat from our bodies, and it causes the water, then the hydrogen bonds to break, and the sweat or the water evaporates. So remember when we talked about in chapter 2 the changes of states, going from a liquid to a vapor is an endothermic process. It takes energy to evaporate or to turn liquid into vapor. So where is the sweat getting the energy? It's getting it from our skin and taking it away. So that is what we call evaporative cooling. So all of these unique properties that we've talked about with water are all related to the hydrogen bonds that happen between water and how much energy it takes to break those hydrogen bonds. This is showing our water when we go to heat it up. So here's somewhat liquid water. We turn on the Bunsen burner. We're giving it heat energy, so the water molecules, you're going to notice, are going to start moving around with more kinetic energy. And at some point you give it enough energy to break the hydrogen bonds and they turn into vapor and they start to boil. Now we've got a picture of liquid water and we're going to show you freezing it. So we're going to fill up our ice tray with liquid water and we're going to put it in the freezer. And then you tell me, does liquid water turning into solid ice cubes, is that an endothermic process or an exothermic process? Well, going from a liquid to a solid, it's easier to remember the other way around. When we melt a solid to a liquid, well, we have to put in energy to get our ice to melt. So going the opposite direction from a liquid to a solid, energy has to be given off. It has to exit to freeze water. So that's the job of the freezer, is to pull the heat energy out of our water molecules. So let's go ahead. I want to show you this one more time. I want to focus on. So let's focus our attention on the water molecules. So let me put the water in the freezer, and what you're going to notice is water, when it freezes, it actually expands because of the unique property how water can hydrogen bond to 4 neighboring water molecules. As you cool down liquid water and those water molecules stop moving around so fast, what they do is they form these hexagonal shapes. You end up with this hexagonal hole inside your frozen water. So this is unique to water. Most substances on planet Earth, when you freeze them, when you go from a liquid to a solid, they get more compact. The molecules, stop moving around with much kinetic energy. They slow down, so they're able to pack together tighter. But liquid water will actually expand when it freezes and form these hexagonal holes, which make it less dense. So because the water now has more air inside, more empty space, it's less dense, so it's able to float on top of liquid water, which is a good thing, because if ice became more dense when it froze, if you had a lake, right now when a lake starts to freeze, the water will float on the top, which allows the vegetation and the marine life to continue living underneath the top layer of ice. If ice was more like other substances on Earth where it's more dense than water, it would float to the bottom or sink to the bottom, and then eventually your whole lake would be solid ice and all your fish would die. So we're pretty lucky that ice floats. Let's go ahead and zoom in on ice and zoom in on water. So if you notice, sure enough, liquid is more compact than our ice. Ice is less dense.